Random processes with reinforcement arise in a varied range of contexts. These are examples where the entire trajectory of the process will contribute to its eventual fate. Polya's urn is perhaps the most well-known example. We shall here describe some results from the study of a system of interacting urns positioned in a circle and where balls of different type annihilate upon contact. Motivation for the study comes from its connection to competition in a planar growth model with reinforcement. The analysis will lead us to study an auto-adverse growth model on a cycle, which can be perceived as an expression in a discrete setting of the geometry of a Möbius strip. So consider a cycle of length n and imagine an urn positioned at each vertex. Position balls of k larger than or equal to 2 different types into urns so that no urn contains more than one type. Each ball is assigned a Poisson clock, and when the clock rings, it sends a copy of itself to each neighboring urn. Balls of different type are not allowed in the same urn at the same time and annihilate on a one-to-one basis. Ahlberg, Griffiths, Janson and Morris show that for k equals 2 and any non-zero initial configuration, the system will eventually almost surely consist of a single surviving type. The same was found to hold for k equals 2 and any finite connected graph. However, for k greater than or equal to 3, there are graphs where coexistence occurs with positive probability. Here's an example of such a graph where it's easy to realize that if red, blue and green are located at the outside vertices, it's hard for either of them to dominate in the middle. In the same paper, the authors conjecture that, at least for the cycle, competition between more than two colors should again have a single surviving type. This conjecture has now been established, so for every n larger than k larger than 2 and any non-zero initial configuration, the k-type competing urn scheme on the cycle of length n has almost surely a single surviving type. Let us describe briefly some of the elements that goes into the proof of this theorem. For initial configurations consisting of a single type, the competing urn scheme corresponds to a multi-type branching process in continuous time. For k equals 2, it is possible to encode red balls as +1s and blue balls as -1s, and thus express the evolution of the process as the difference between two dependent branching processes. However, this approach becomes problematic for k larger than or equal to 3. Here's how we can deal with a larger number of colors. Given a configuration of balls, we shall refer to a maximal connected monochromatic subgraph as a tribe. When the number of tribes is even, we can still encode tribes alternatingly by positive and negative numbers. Since tribes at distance 2 do not interact, this will be a correct description of the process until these tribes meet. When the number of tribes is odd, an encoding into positive and negative numbers will not be enough on its own, because the first and the last tribe would receive the same sign and appear to be of the same type, while in fact they annihilate. However, an encoding, together with a sign reversing edge, an edge where particles jumping across the edge reverse their signs, that will maintain the dynamics of the process. The process that arises from the introduction of a sign reversing edge has an auto-adverse behavior. Consider a process started with a single particle. As its descendants make their way around the circle clockwise, the signs are negated. Completing yet another lap clockwise, they return with the original sign. It is as if they live on an object of twice the length. Let Z of t denote the configuration of particles at time t. That is, Z of t is an integer vector. Let A star denote the matrix obtained from the adjacency matrix of the cycle, but with its northeastern and southwestern corners negated. If at time t a clock rings at position k, then we can express the difference in the vector z by the kth column of the A star matrix. This explains why the evolution of the vector z will be determined by the eigenstructure of the reinforcement matrix A star. We find the geometry of the Möbius strips expressed in the eigenstructure of A star, in the sense that a vector v is an eigenvector of A star if and only if v minus v is an eigenvector of the adjacency matrix of the cycle of twice the length. Analyzing the eigenstructure of the reinforcement matrix, we find that the largest eigenvalue equals 2 cosine pi over n and has multiplicity 2. The corresponding eigenspace is spanned by harmonic functions. By analyzing the martingales that arise, we prove that the auto-annihilative growth process on the cycle, once properly rescaled, converges almost surely to, again, an harmonic function, with a random magnitude and a random shift. Note that the limiting profile describes a configuration with a single tribe and a single edge where competition occurs. Hence, irregardless of the initial number of tribes, eventually there is only a single one left. From this observation, we are able to conclude that coexistence cannot prevail in the competing urn scheme on a cycle.